Now we're going to move on to a handy little trick that we can use so we don't have to calculate rotational inertias over and over and over. Okay? This little trick is called the Parallelaxis Theorem. And honestly guys, this is going to get you through just about every problem that we do in this class when it comes to rotational inertia. If you memorize the Parallelaxis Theorem, if you know the trick, then now you don't have to memorize a whole bunch of formulas. So I highly recommend memorizing the Parallelaxis Theorem. It's really straightforward. So we did the rod that had the rotational axis straight through the center. But what happens if we change that? What happens if we move the rod, the rotational axis along the rod? So now we're going to have the rotational axis here, and we're going to put it on the end of the rod. So this means that we still have a rod, mass m, length L. This means that now we would have to set up an entire new integral in order to solve for this rotational inertia. So the integral stays the same. Check the previous video to take a look at what the integral should be at the start. It should start out as the integral of x squared m over L times dx. Okay? This was what we used to get rid of that dm term because we're integrating over mass. Technically, we wanted to integrate over length. This x squared term comes from the r squared term, our distance away from the rotational axis. And in this case, we are using the x-axis as our determining factor there. Now we're going to be integrating from 0 to L, the full length of the rod. So we're starting at 0, we're starting at x is equal to 0, we're moving to L. And that's going to give us, we do the integration, mx cubed over 3L from 0 to L, and we get a rotational inertia of ml squared over 3. Again, this one's not too bad, but it's going to get really complicated as we start to make these problems more and more complex. I guess that's kind of moronic for me to say, but it's going to get more and more complex as the geometries get nastier. What happens if I maybe start to tilt this thing in addition to moving it away from the rotational axis? Now I'm making life really, really hard on you guys. That's where the Parallelaxis Theorem comes in. And what the Parallelaxis Theorem tells us, what this tells us is that we can set up our rotational inertia equation based off of the original rotational inertia equation based around the center of mass. So if you look in your textbook in chapter 10 on that table, you'll see that each one of those rotational inertias is based off of the center of mass of the object. So you take what's in the table, the I as given by the center of mass, the rotational inertia given by the center of mass, and you add to it mh squared. mh squared. So take what's in the book, the geometry inside the book, and add mh squared. M stands for the total mass of the object, which you have to use anyway when you're calculating the original rotational inertia. And then h is the distance of the center of mass, rotation, to the new axis. Okay? So what we're going to do is we're going to move the axis of rotation from where it is in the diagram on that table. We're going to move it, and h represents that distance of the movement, the distance of the center of mass to the new axis. Okay? So let's take this example that we just did, as Wesley shakes his collar. Let's do this example that we just did, going from 0 to L. Now let's set it up using the Parallelaxis Theorem. In the original diagram, you had this, L over 2, total mass m. And we calculated this in the previous video as Wesley, you're making it very difficult for Daddy to lecture, ml squared over 12. So that's what we found when we did that in the previous video. Now we shift the rotational axis over to one of the ends of the rod. So now it looks like the picture here. That movement is a distance of L over 2. It's half the length of the rod. So that's our h value. So this means that this is our center of mass value. This stands in for this guy, what we originally calculated. And now we add to that, m multiplied by h, which is the distance that we've moved the rotational axis. we've moved it a value of L over 2, and then we square it. Okay? That is going to give us ml squared over 12 plus, that's going to be ml squared over 4. And you guys will see, once you find a common denominator there of 12, this is going to go to what? 3 ml squared over 12 plus ml squared over 12. That makes 4 ml squared over 12, which is the same thing as 1/3 ml squared. Okay? So you guys see that we didn't have to do any integration as long as we used this parallel axis theorem. What makes this so confusing for students the first time is this idea of moving the rotational axis. So we start out with the diagram in chapter 10, okay, the big table that's going to have all of those values. And then we're going to shift the rotational axis to where it needs to be in the new type of geometry, the new rotational axis that this whole thing's going to circle around. That is your h value right there. M is the total mass, and this I, center of mass, the original rotational inertia, is what you found in the table. Okay? Now, 2 quick examples. Let's take a hoop, and my diagram's pretty bad, and I apologize for that. But now let's take a hoop, and instead of rotating it around its center, let's shift the rotational axis down. Okay? And the hoop has a radius r. Now, if you look in your book, the hoop center of mass rotational inertia is equal to mr squared. That's when we have the rotational axis going straight through the hoop, like the dotted line. So the hoop is kind of spinning on itself. Now we shift the rotational axis to the end of the hoop, which is a distance r. So now the new rotational inertia is the original rotational inertia, mr squared, plus the new rotational inertia based off of this shift, which is going to be m multiplied by what's h? H is r, that's where we've shifted from the center of the hoop to the end. So it's mr squared again, and you get an I equal to 2mr squared. Okay? That one's pretty easy. Now let's take a solid cylinder. This is different from a thin rod. A solid cylinder. It has a radius r, and it has some mass m. And we're going to shift from the center. The rotational axis is going to be a distance of L over a quarter, or a quarter of L. L over a quarter would be different. So 1/4 L. So we're going to take the rotational axis from the center, and we're going to shift it a distance of 1/4 L. Okay? If you look up in your table, you'll see that I, center of mass, is equal to 1/4 mr squared. 1/4 mr squared. Plus, there's actually a second part to it, plus 1/12 ml squared. So it actually has 2 parts, which I forgot. For a solid cylinder, it's 1/4 mr squared plus 1/12 ml squared. Okay, so it has 2 portions to it. Now we need to add the shift to it. So the new I, the new rotational inertia, is going to be equal to 1/4 mr squared plus 1/12 ml squared plus the shift, which is the total mass of the object, m, multiplied by the shift value. It was here, that's what gave us these first 2 terms. It was at the center. Now we've shifted it a quarter L, so that's going to be L over 4 squared. Okay? L over 4 squared. Let you guys do the math on that one, but you should get that the rotational inertia is equal to 1/4 mr squared plus 7 ml squared over 48. Sorry, this got a little messy. Again, guys, you don't have to worry so much about memorizing all of these different types of geometries. There are an infinite number of places that I can put the rotational axis to create different rotational inertias in different types of problems. Okay? It's impossible to know all of them. But what you can know is the basic one that you start with on the table, okay? Start with it on the table, and then shifting it appropriately, and that stands in for your h value here. So take a geometry that you know, figure out the distance that you're shifting the rotational axis, and then you just add in this mh squared term. It makes life really simple. And on the AP test, again, they're not asking you guys to calculate rotational inertias. They're not asking you guys to do that. They may be interested in solving some problems with rotational inertias, and you may have to use the parallel axis theorem, but they're not going to go out of control on you. Okay?